Sample exam 7, problem number 19. For the data x1, y1 equal to 1 and 2, and x2, y2 equal to 5 and 3, and the model, the expected value of y equals beta x, the least squares estimate of beta is... Answer to question number 19. We're given that it's a linear equation, and it says expected value of y is equal to beta x, and that's because usually this is expected value of it is 0, so it goes away. And we're going to find two different ways to solve this. First one is find the least squares. So the error is this term, so if you take that beta over, y minus beta x is the error, and we want to find the least squared error. So that's what this quantity is, and it's summed over each data point. Now to minimize this, we take the derivative with respect to beta, and we get 2 times this times the chain rule, which is minus x. We set it equal to 0. We solve for beta, and we get this. Then we plug in the values that we have, and we get 17 over 26. Now the second way to do this is just, since there's only 2 data points, we just plug them in. So to this equation here, we only have 1 to 2, and so there's 2 of these, and that's what these represent. And so this is a y, and the x is 1, and this is a y, and the x is 5. So then if to minimize this, we take the derivative, we get this, set it to 0, solve for b, and we get the same number. Number 20. Let x1 through x4 be a random sample from the discrete distribution x such that the probability of x equals this quantity and 0 otherwise for theta greater than 0. If the data are 17, 10, 32, and 5, what is the maximum likelihood estimate of theta? Now in number 20, we want to find the maximum likelihood estimate. Okay, so first of all, we have to find the joint distribution of the data. There's 4 data points, and then so it's the product of these. Since it's a random sample, they're independent, and so it's the product of the individual densities, which then we get this. The maximum likelihood estimator, it's easier to take the log of it, since the log is a one-to-one function. To maximize this is equivalent to maximizing that. So you take the log, and then that comes out in front. The e and the natural log go away, and then divided by, you can minus it in whenever it's the log, and we have this. Now we take the derivative with respect to theta, and we get 1 over theta times this constant. Here we get 8 theta, set it to 0. Solve for theta, and you get 4. Well, you get this, but then plug in our data, and then it ends up being 4. Number 21, let x1 through xn be a random sample from a distribution with density function f of x equal to this quantity, x between 0 and infinity and 0 otherwise. What is the Rao-Kramer lower bound for the variance of unbiased estimators of theta, i.e. the minimum variance bound, given that the expected value of x cubed is 1 over theta, and the expected value of x to the 6th is 2 over theta squared. So number 21, find the Rao-Kramer lower bound, and this is one of those things that you're just going to have to memorize, and this is the equation, and this ends up being the answer to the problem, but we'll go through that below. To derive this on the test would take a little more time than what you're given. Well, you could do it in the allotted time, but you wouldn't be able to finish the rest of them. So it's just easier to memorize that. So we're going to break this down into each piece. First, we're going to take the log of our distribution, which is this. So the 3 theta x squared, the 3 I'm lumping in with this, because when we take the derivative, that's a constant and it goes away. So then divided by not divided by, it's e raised to the minus theta x cubed. So the e and the natural log go away. So this is it. So that's this piece here. Now we need to take the derivative of that with respect to theta. And that's what we do here. So the derivative is 1 over theta, and then that's just minus x cubed. Then it says square it. So we square this, and we get this equation. Okay, so that's this inner piece. Now it says take the expected value, and that's in regards to x. So we take the expected value of this, and in regards to x, this is a constant, so it comes out of the expectation, and then the 2 over theta minus 2 over theta comes out, and so it's the expected value of x cubed, and that was provided, and then it's the expected value of x to the 6th, which they provided, which is this. Add that, you get this. So 1 over theta squared is this piece right here, which is this. And then it's times n, invert multiply, you get the answer. Number 22. Let P represent the proportion of defectives in a manufacturing process to test the null that P is less than or equal to 1/4 versus the alternative that is greater than 1/4. A random sample of size 5 is taken from the process. If the number of defectives is 4 or more, the null hypothesis is rejected. What is the probability of rejecting the null when P is equal to 1/5? Now, number 22. What's the probability of rejecting the null when P is equal to 1/5? So to reject, we have to be greater than or equal to x, given that the true P is 0.5. Now, since we only have a sample of size 5, being greater than or equal to 4 means that we equal 4 or we equal 5, so we're going to add those two together. And since this is a binomial with the true proportion 1/5, we get this plus that. Combine those to this, and you get 21 over 3,125. Number 23. Let x have the density function f of x equal to that. The hypothesis, I actually think there's an error here. Let the null hypothesis that theta is equal to 1 is to be rejected in favor of the alternative, theta equal to 2, if x is greater than 0.9. What is the probability of a type 1 error? Now 23 is what's the probability of a type 1 error? And a type 1 error means you reject when you shouldn't, and they tell us that you reject the null hypothesis if x is greater than 0.5, and there's a 0 here, which means that we're assuming the null hypothesis is true, which means theta is equal to 1. So to find this probability, we integrate from 0.9 to 1, which is the sample space, and we plug in theta 1 equal to 1 into the density. Integrate, we get 0.9 or 19. 24. An urn contains 4 balls numbered 0 through 3. One ball is selected at random and removed from the urn and not replaced. All balls with non-zero numbers less than that of the selected ball are removed from the urn. Then a second ball is selected at random from those remaining in the urn. What is the probability that the second ball selected is numbered 3? Number 24. This is kind of a neat problem. We want to find the probability that on our second draw, so that's x2, on our second draw we get the number 3. So the way we do this is, or the way I think about doing this, is we introduce what happened on the first draw. So this probability is equal to this. So this says, what's the probability that this on the second draw we have a 3, and you know, and then we sum over all possibilities, meaning that we had a 0, a 1, a 2, a 3. And so this doesn't change this probability. And then this can be rewritten in this form. The sum is still the same. So now we expand this. We let I equal 0. So we get the first draw is a 1 times the probability the second draw is a 3, given that the first draw is a 0. And we do that for each of these. And so the last one is a 3. So we put in a 3 here and here. And now the problem becomes easy. What's the probability we would draw a 0 on the first one? 1/4. And then we take out all non-zero balls less than that. It means there's 3 left. What's the probability we draw a 3 is this. And this one is if we drew a 1 on the first one. So the probability we draw a 1 is 1/4. There's 3 balls left, so it's 1/3. Here we draw a 2. Probably drawing 2 is 1/4, but we have to take out the 1 and the 2, so there's 2 balls left. What's probably we draw 3, a 1/3, and then here we draw 3, take them all out. There's no way that we can draw a 3. So the answer is 7/24. Number 25. An urn contains 4 red balls, 8 green balls, and 2 yellow balls. 5 balls are randomly selected with replacement from the urn. What is the probability that 1 red ball, 2 green balls, and 2 yellow balls will be selected? So number 25 is a classic multinomial problem where the probability of drawing a red ball is 4 out of 14. The probability of drawing a green ball is 8 out of 14. The probability of drawing a yellow ball is 2 out of 14. Now, yes, I could have reduced those to 2/7, 4/7, and 1/7, and actually that's how you get this denominator. But I left it like that to show you that you have to normalize those so they add to 1. So here you're drawing 5 balls, and we want 1 red, 2 green, 2 yellow. So then we put the same number up there. We crunch the numbers. We get 960 over 7/5. Number 26. 2 numbers are chosen independently and at random from the interval 0 to 1. What is the probability that the 2 numbers differ by more than 1/2? Now, this one also is a neat problem. So here we're going to draw 2 random numbers from a uniform distribution 0 to 1. We want to find the probability that that this difference is greater than 1/2. Now, remember when you're dealing with absolute value being greater than a number, that's the equivalent to this, that this is greater than 1/2 and x2 minus 1 is greater than 1/2. And if we draw a picture, it looks like this. So here's x1, here's x2. The only way that we can have a difference of greater than 1/2 is we're in one of these 2 regions. They don't intersect, so you just add this probability and add this probability. Okay, and so that's what this is saying here. Now, since these are triangles, this base is 1/2, this base is 1/2, so this area is 1/2 times the base times the height, which is 1/2 cubed. And the same way for this one, this area is 1/2 cubed, which ends up being 1/4. Okay, well, that's all I have for today. I hope you enjoyed the video. Please like it, subscribe so you don't miss the next one. Thanks, bye.